If you only benchmark the die, you are measuring the known product. An AI chip becomes useful only when memory can fit it. Interconnector can scale it. Software can schedule it. Packaging can cool it. And customers can keep it busy. Introcorp Bias is updating every week with a new industry insight. The channel connects technical design choice to supply chain structure and business outcomes. Recurring features cover chip architecture, semiconductor IP, EDA, and tape-out chiplets and die-to-die links, HBM and advanced package, cloud custom silicon, system automation, and AI infrastructure economies. Subscribe if you want to one concise technical briefing each week and use the comments to suggest the next feature topics. The industry is often drawn as a linear chain, but the competitive reality is a loop. Workloads define the architecture. Architecture selects IP, EDA flows, process technology, memory, and the packaging. The package becomes a system. The system becomes a fleet. And the fleet behavior produces the authorization and failure data. Net shape the net design. Net feedback matters because the product boundary has expanded. A merchant accelerator vendor may optimize from compiler to rack. A cloud provider may co-design a chip with its scheduler and workload mix. A foundry or IP supplier wins by becoming difficult to replace inside this loop. When evaluating a company, ask which feedback it sees first and which decisions it can change fastest. Training and inference use similar primitives, but they optimize different object functions. Training wants to finish a model sooner, so global throughput and scale efficiency dominate. That pulls the design toward dense mass, high bandwidth memory for model and optimizer state, and fabrics that keep collective communication from storing thousands of devices. Inference wants to serve useful tokens at the required latency and the cost. Memory capacity for KV cache, decode efficiency, batching routing, and free availability can matter more than headline peak operations. This is why a single benchmark can mislead. Start with a workload shape, model architecture, precision, sequence length, batch behavior, latency target, and deployment scale. Then choose the silicon. Chip design is a sequence of commitments. Early choices workload, data flow, memory hierarchy, and interconnect are cheap to change on paper and expensive to change after RTL. Integration and verification convert architectural intent into a testable design. Physical implementation turns that design into geometry and corrosive timing, power, signal integrity, and manufacturability. Sign-off is final evidence before tape-out. Then the work continues. Package, board, firmware, compiler, and silicon bring up. Reusable IP and EDA automation compress the schedule, but they do not remove system risks. Every stage keeps asking 4 questions. Does it need PPA? Can it be verified? Can it yield? And can software actually use it? Semiconductor IP is not one thing. It ranges from instruction set, license, to synthesizable RTL, a silicon-proven physical interface, a complete subsystem, or the tools and reference roles around it. In this conceptual accelerator, compute may be differentiated. Higher CPU security, SerDes, HBM PHY, and die-to-die interfaces are integrated from partners. They can remove years of work, but the risk moves into integration, process portability, verification coverage, supply roadmaps, and commercial terms. Business models combine upfront license, per unit royalties, portfolio subscriptions, and engineering service. The key diligence question is not build or buy. It is which blocks create differentiation, which blocks must be proven, and where does dependence become strategic. This reference drawing shows why the package is now an architectural object. Compute dies sits beside stacks of high bandwidth memory on an interposer or redistribution layer. Above a package substrate that distributes power and escapes signals to the board. The supplier handles coverage here. Foundry wafers, now good dies, HBM stacks, interposer capacity, assembly, test, substrate, cooling, and system qualification. Chiplets can improve modularity and reduce the risk of one giant monolithic die, but they add interfaces package complexity and thermal constraints. Capacity must be aligned across several suppliers. Extra wafers are useless if HBM or advanced package is unavailable. The design unit is increasingly the package and often the rack. The business matrix is not peak FLOPS. It is the cost of producing a useful result require quality and service level. A simple framing is per phone cost divided by useful tokens served. The numerator includes silicon yield, HBM and the package, both networking, facilities, power, cooling, depreciation, and the non-recurring cost of design and software. The denominator depends on realized throughput, utilization, availability, and model efficiency. This explains why full stack control is powerful. The operator can measure idle time, communication stalls, failures, and the workload mix. Then tune the compiler, scheduler, topology, and next silicon generation. A cheaper die can lose to a system that stays busy and delivers more useful work. 4. Archetypes organize the business landscape. Merchant platform companies sell accelerator systems and software. Their mode is ecosystem and repeat product cadence. Cloud providers design custom silicon to lower internal cost and differentiate a service. Their advantage is workload and free data, but the developers must adopt the tool chain. IP and EDS price monetize rights, subscriptions, loyalties, and trusted design flows. They win by being designed in early and reused broadly. Foundries and advanced packaging providers sell process technology, capacity, yield learning, and manufacturing execution. The reward is strategic centrality, balance against enormous capital intensity. Most real companies combine models. The key is to identify the control point that produce pricing power and compounding learning. The most durable mode may begin as a bottleneck. That's design talent and EDA expertise create schedule advantage. Leading edge yield create cost and capacity advantage. HBM and advanced packaging create system delivery advantage. Power and cooling determine where racks can be deployed. Software and authorization determine where expensive hardware becomes productive capacity. But scarcity alone is not a mode. The mode forms when volume generates learning. Learning improves the product, and the improvement attracts more volume. That is the loop to watch on Introcorp is. The next exposure can unpack HBM and the memory wall, chiplets, and UCIe, inference economy, and custom cloud silicon. The recurring question is simple: who learns fastest from deployed system? This is the end-to-end map. Workload shams architecture. IP and EDA compress the design cycle. The supply chain coverage inside the package, and the system authorization determines the economy. If this episode helps you connect the layers, subscribe to the Introcorp for a new industry insight every week. Give the video a thumbs up so it can reach more engineers and builders. And leave a comment with the AI chip topic you want next. HBM, triplets, EDA, custom silicon. Thanks for watching, and I will see you in the next one.